Hello, my name is Kevin Puklicz. I'm a field application engineer here at LMI Technologies. Today, we will be exploring the capabilities of GoPxL with a focus on our new surface anomaly detector and how we can deploy AI models on our GoMax series. One of the parts I will demonstrate the surface anomaly detector on is a waterproof automotive wiring harness connector. It's a crucial component designed to protect electrical connections in vehicles from moisture, dirt, and other environmental factors. These harnesses are typically made with durable, weather-resistant materials and sealed connectors to ensure reliability performance in the harshest conditions. Our inspection will verify that the connector has been made properly without any surface level defects. Getting started, you can see I'm using our GoMax Orin Plus, and we're running our firmware 1.1.52.14, which contains our surface anomaly detector tool. I currently have a 2630 Gocator connected to my GoMax. The Gocator 2630 was chosen for this application because of some essential features for the surface anomaly detection. Things like high dynamic range, or better known as HDR, and our ability to capture up to 4,000 points per line. HDR enhances visibility by capturing a wider range of light, making subtle defects more detectable, while the high density of data points provide detailed surface profiles crucial for accurate anomaly detection. The rich data set significantly improves AI performance, leading to better training and more reliable predictions. Industries like automotive are already benefiting from this technology, enhancing their quality control processes and overall product quality. Once connected, we will navigate to the scan page. We will be capturing surfaces with intensity in this demonstration. Please refer to another YouTube video on how to set up and configure these settings. To start our surface anomaly detection training, first we need to image good parts. So what we will do is we will capture images of parts without defects. So I will turn on record. I will start my camera and I will only capture images of good parts. As we can see, my frame index is increasing. You'll want a minimum of 20 good surface images. For this example, I had about 40 good surface images to work with. Once the minimum requirement for good parts that have been scanned, you can go ahead and stop the sensor. And what you're going to want to do is download the replay file from the GoMax. This will download a .gprec file. We will want to rename this, illustrating that it's scans of good parts that we will use later on. While we are here, we'll want to capture images of not good parts as well. So first, clear the buffer of frames. Repeat the recording of scans, and now capture bad parts or images of connectors that have surface level defects. We will capture as many surface level defects as we can to later feed into our surface anomaly detector tool. If this is a new installation and we did not have any parts with defects available to scan, we could train the anomaly detector tool on good parts only. We will discuss this option while configuring the training wizard and the parameters later. Once all good images are captured and all defect images are captured and saved locally, you can see I have my good images saved here as a .gprec as well as 10 defects as a .gprec. I'm going to save these for later once I bring in our surface anomaly detector tool. Now jumping into creating a job file, we will then navigate to the tools. We can stop our camera. We can put our GoMax into replay mode. The great feature of the surface anomaly detector tool is it runs in replay mode on all GoMaxes running the anomaly detector firmware. To run on a live sensor, you'll need to purchase a dongle from LMI Technologies. Now that we have all of the recording files that we needed, we can jump into our job file. Here I'm in AD training demo. Bringing in my replay data, I can start to apply my tools. Using a surface bounding box, we will find the connector in 3D space. We will locate the center XY as well as fit a box around our connector. Using the center X of our bounding box, we will now fit a plane to the outermost surfaces using 4 regions. The surface bounding box and surface plane allow us to correct for any rotation or distance change while imaging the connector. This will better feed our 3D data into our surface anomaly detector tool. Jumping into our surface anomaly detector, we're bringing in the transformed surface. As well, we can select our model here, and now we can launch the wizard. Once in the wizard, either upload a project that's been completed or start a new project. Once a project is created, we can continue to the next page. In this page, we're going to create 2 models here, one for surface level defects and one for intensity level defects. Again, creating a new model. Now upload the frames. Selecting this icon will upload the frames in your memory buffer. So now we can see all the frames that were in my memory are now uploaded to the wizard. These were all my good frames, so I will select all, and coming to this user label, I will select OK. This will label all of them. Although I know frame 5 has a defect, I can come in here, select it, and set it to not good. We also want to upload some not good images. So choosing the icon next to upload from memory, we can upload from disk. Selecting here, I can select my defective surface level images. You can see they've now been uploaded to the bottom. I can now label these as not good. So now I have approximately 48 images of good and not good images. If we wanted to download this entire image set as a single rec file, we could do that by selecting this icon. If we want to delete frames, we can select the frames we want to delete and use the delete icon. This is handy if you want to make sets of just good images and you didn't have control of the images that you were scanning. This last icon is auto split. What auto split does is it sets good images for training and not good imaging for testing, and it does a percentage of those images. We recommend 80% of the OK images in train, 20% of the OK images in test, and 100% of the not good images in test as well. Looking at our frames, we can see that the image 5 that was labeled not good is set to test, as well as 80% of our good images are set to train. And then at the bottom, all of our not good images are all set to test. So now we have our model selected. We have enough frames to test and train our model. We will continue on to train model. We can see it's counted the number of good images as well as the number of bad images. For data source, we're going to choose surface for this model. As for resolution, select 256 by 256, or if you want more resolution, you can go to 512 by 512. Anomaly size in this instance, we're going to set to big. If we needed more resolution out of our model, we could apply tiling. Tiling will help divide our image up. So if we wanted to horizontally tile, we could then split the image into 256 by 256. We could also split it horizontally as well if we want more resolution in each corner. A homogeneous part has uniform or consistent characteristics across its surface. For example, a flat metal sheet or a textured panel where the pattern repeats. For these parts, tiling works well because each section looks similar, and the system can divide the image into smaller tiles and analyze them independently, making it easier to spot deviations from the expected uniform appearance. For this application, we are not going to tile. Image augmentation is a powerful technique when you have a limited data set for training. By applying various transformations like rotation, scaling to your existing images, you can effectively multiply your training data. This creates more diverse examples for the system to learn from, helping it become more robust and better at detecting anomalies. even when starting with just a few original training samples. We have augmentations per frame, which is the number of augmentations generated for each frame. Border erosion performs erosion and dilation operations on each frame. Dropouts removes data points randomly to simulate low exposure up to the specified percentage of the original scan data. And then we have rotation around our X, Y, and Z axis, as well as translation on our X axis and Y axis. And then scale is used if the part grows or shrinks in size. Moving on, we have synthesize bad frames. When selecting synthesize bad frames, the system automatically generates synthetic defect examples by applying various artificial anomalies to good sample images. These synthesized defects might include digital artifacts like random noise patterns, localized brightness changes, or subtle distortions. While these artificially create defects aren't visible to users during normal operation, they help the system learn to distinguish between normal variations and potential anomalies, improving its detection capabilities. As well as we have advanced parameters. In advanced parameters, we have batch size. This is the number of frames in a batch. You can decrease this value if you're using a model with more resolution, the 512 by 512 resolution, or tiling. Epochs, this is the number of times the entire data set passes through the training algorithm. Increase this value if the loss function is not converging. We also have early stop. If this is enabled, the tool will stop training before the total number of epochs is completed, if the model's performance stops improving and plateaus. And then we have our backbone, clamp, and learning rate. The backbone is the feature extractor used by the tool. The clamp is the range within the data value should be clamped. Lower this value if your charts are not converging. Lastly, we have our learning rate. This is the speed at which the model learns. A higher value causes the model to learn more quickly with bigger steps, versus a lower value causes the model to learn more slowly. This can be potentially more accurate, but if the value is too low, the model can get stuck. Once these settings are selected, we can move on and start training the model. When monitoring training, the loss function graph typically shows how well the model is learning by plotting the error over training iterations. A steadily decreasing loss indicates good learning progress, while plateaus suggest the model may be struggling to improve further. The AUROC, or area under the receiver operating characteristic graph, displays the model's classification performance across different threshold values, with higher values closer to 1 indicating better discrimination between classes. Watching both metrics together provides complementary insights. While loss shows optimization progress, AUROC reveals the actual predictive capability. Warning signs include loss that increases, overfitting, or an AUROC that drops on validation data compared to training data. Now that our training is complete, you can see we had an early stop at 9 epochs. That's because both of our graphs have plateaued. Going next, we can now test our model on our fed images. As we can see, our prediction here, the score, as well as our label. Now that the training's been completed and we're happy with the results, we can now exit the wizard. Once the wizard is closed, we can select which model we want to run in our surface anomaly detector tool. It should be noted, it's crucial to maintain identical pre-processing steps between training and inference phases. The exact same tool chain, including all image adjustments, filters, and transformations, must be applied in both stages. Any differences, even minor ones, can cause the system to generate false positives or miss actual defects. This consistency ensures that the system compares the images under the same conditions it was trained on. So here we can see our model now. We have the available models that we've trained. So the surface model is here. This running, we now get an anomaly surface, we get an anomaly threshold, we get the intensity threshold. If it's an anomaly, this will be a Boolean value of 0 or 1, and then our anomaly score, as well as our anomaly map, and as well as our heat map. Now I'm going to load images with defects to highlight these values changing. Now I've loaded surfaces with surface level defects. Going to an image where there's a clear surface defect here, we can see that we are flagging that's an anomaly. Our score is quite high, and our intensity threshold is 174. Using this, we then add a surface blob tool. The surface blob tool, we will feed in the anomaly detector surface, anomaly surface. Once that's selected, we then turn on use intensity. Using intensity, we'll then set the threshold to the value that our anomaly tool has told us to, which is 174. Again, that is this value here. We will say anything above that value is a blob. We can leave all these kernels set to 3. We will turn off the area filter, turn off any aspect or circularity filter, and what we will do is we will turn on enable array output, and then we will also turn on show precise boundary. Here we can see we are now finding the anomaly in that surface. As well as here's another one where we're finding the anomaly on this surface. Here we're finding an anomaly inside the connector, as well on the surface here. Going back to the surface anomaly detector tool, we can actually take a look at the heat map here, and we can see that our model is working correctly, and we're highlighting the surface level defect that we can see in our surface data here. Now that we've trained our surface anomaly detector on all of our surfaces, we're going to train an additional model that focuses on intensity data. The images that we took with not good parts had surface level defects, as can be seen in our data viewer here. Now I'll upload some defects that are only seen in intensity data. Here, looking at our data, we can now look at an intensity mode. We can see here that this part goes from white to black, which is a defect. We're going to create an additional model that will catch this defect. Going to our next image, we have a different color here versus here, and that's reflected in our intensity values that are calculated here. Well, as here on our black surface, we have some white tape. As well as here, we have a change of color from here to here. As well as here, we have some darker color here reflected in intensity. So here we have a change in intensity on this corner, as well as here on the connector, as well as this whole connector here. So now utilizing these 8 not good frames, we can train an additional model. Coming into the wizard, we're going to launch it again. We're going to go into the existing project that we've already made. This time we're going to select intensity model here instead of surface model. We can reuse all the good frames that we used in our last training. I'm going to remove these 8 images here that were surface defects. So here I'm going to utilize the delete frames function. Now that I've deleted the surface defect frames, I'm going to add the intensity defect frames. So using my upload from disk here, I'm going to select my intensity defects. This will act just like training a surface model. Select the intensity defects, select these 2 not good. Again, we can use our auto split. This will set 80% of the good images to train, 20% of the good images to test, as well as 100% of the not good images to test. Now that we have our intensity model selected, we'll now train this model. This time, instead of using our surface as our source, we're going to use the intensity. Again, we're going to use the same resolution. We're going to keep anomalies size small and big. We will practice some augmentation, as well as we'll keep on synthesize bad frames to help aid in our thresholding. I'm going to start the training again. Training time for surface and intensity-based models depend on several key factors: the complexity of the model, the dataset size, and the enabled features like augmentation and synthetic data all impact the duration. While augmentation and synthetic data creation can extend training time due to additional processing required, they typically result in more robust models. Training times vary significantly across hardware platforms. This can be from several minutes to up to an hour, depending on whether you're using a GoMax NX, Orin, or the much faster Orin Plus. Now that our training's complete and we can see that our two graphs are converging, we can move and test the images that we fed. We can see our prediction, the score, as well as our label. We can see our models picking up the defects that we fed. Once we're happy with the model's performance, we can close the wizard. Now that we have two models trained, we can now select in our surface anomaly detector tool. Here we're using the surface model that we've trained and configured, and I added a second tool now that is surface anomaly detector intensity. And in here I'm going to select the model that is the intensity model. So now once this gets transitioned to real time and uses a dongle to run, not in replay, we will have not only a surface model running, but also an intensity model. The images that I'm displaying now, if we go to our first image, where this defect will only be caught by the intensity model, as we can go to here, we can see that our is an anomaly is 0. So this model is not picking up that there's anything wrong with the surface, but our intensity model is saying, nope, this is an anomaly. And if we go to our surface blob tool, like we set up with the surface, we just have to pay attention that our intensity threshold this time is 156. So we add an additional surface blob tool. Here we're feeding in the surface AD tool, but the intensity model and their anomaly surface. And then here we will use this value of 156 in here. We will set this to 156. This now highlights all the defects that are coming through the intensity model. So as we can see, this is picking up the change in color, whereas our surface model would not. Go in here, we can see that this surface intensity is a different color. Here we're picking up the tape on the side, as well as the color distortion there. Here we had a black color, as well as here we had a brighter color on the outer shell. Here this connector was much brighter. And here we can see it's detecting all over because this part was actually colored white. Jumping into another example of our surface anomaly detector tool. Here we are imaging LED strips. As you can tell, our LED strip is not flat and has surface level defects. We approach it the same way we approach the automotive connector. We find our surface bounding box in 3D space and we fit a box to it. We locate the side of the LED strip, and here is something that differs from the connector. We're using a polynomial fit to flatten our surface. From here, we're using a feature mask. So we're taking each corner of the bounding box and creating a mask around it. And this one, we are doing a padding of -1 millimeter from the edge. So we're actually pulling the surface in. We use a transform again to center our LED strip. And what's different in this one, I'm using a gap filling filter to just fill some of the dropouts that we got on some of the copper colored surface. Here we did the same approach as our automotive connector. The reason I want to show this one is because we used tiling here. So if we look at our heat map, we can see that our LED strip is set into 2 different regions. So what this looks like for training is, again, we created a project, come into here. I have around 20 images without any defects. And then we have about 14 of defects brought in here. Again, we have two models. We're training on the surface model here. When this is set to surface, we can see that we're still using 256 by 256. Our anomaly size is set to big. Here, we're using tiling because our LED strip can be split into two without losing anything. We can set our vertical tiles to 1 and our horizontal tiles to 2, which will give us more resolution through this training. Here we're now testing our model on the images that we fed, and we can see that it's performing with a positive true rate of 100% and a false positive rate of 0%. This is great. After exiting the wizard, we can then jump into our job file. Again, we have our image that's being fed in. We find it in 3D space. We flatten the image as there's a curve in the strip, and then we feed it into our anomaly surface tool. As we can see here, we have our threshold. We have an intensity threshold as well, and is an anomaly is 1. And then we have our anomaly score. We can feed this into a surface blob tool, which then will highlight the surface defects. So running through my not good image set, we can see that we're clearly highlighting our surface defects. You can see our two tiles clearly on the anomaly image. Again, here we're missing an LED. Again, we can apply the same principle to intensity data. So I went ahead and trained an intensity model as well. We can see from our image that's being fed in, if I turn on intensity, that one of our LEDs is black. So it might be burnt out or discolored. If we go down to our intensity surface anomaly detector, we can see that it's flagging it as an anomaly. And when we go to our surface blob tool, we can see that it's highlighting the LED that is black or discolored, or highlighting a change in intensity. We go to our surface anomaly detector, and we can see that it's not flagging it as an anomaly, because this is the only difference is the change in intensity. So this is a good example of where you might run your images through a surface and intensity surface anomaly detector. Utilizing these two tools, you'll be able to catch both surface defects and intensity defects. Again, we can go back and look at another intensity defect. So here we have a mark on our strip. You can see that we're not flagging it in our surface anomaly detector tool that's running the surface model. But if we go to the intensity model, you can see that we're flagging it. And then going into the blob tool, you can see that we're grabbing that surface where that intensity changes. Again, we can see a bunch flagged here. Going back to our original image, we can see that there was a clear mark on this strip and that we're flagging it. Overall, our surface anomaly detector allows us to catch things that traditional 2D vision would struggle with. This advanced system excels at identifying surface defects and intensity variations with exceptional precision. The model's ability to analyze the line profile data enables faster, more reliable inspection compared to traditional methods, reducing false positives while catching subtle defects that human operators might miss. This technology represents the future of 3D inline inspection, where smart automation meets quality control. Try out this powerful tool today on your GoPxL NX, Orin, or Orin Plus system. We're offering free trial version in the replay mode. For production runtime dongles and pricing, please contact our sales at LMI Technologies. Thank you for watching.